Today, we explore Google Translate, translating text between languages. We'll follow a clear ML system design approach, clarify requirements. Which languages? Enough data? Offline support? Input constraints? Frame as ML task. Input is a source language sentence. Output is a target language sentence. A sec-to-sec problem. Encoder-decoder transformers with attention are ideal. Data preparation. Clean, normalize, handle named entities, tokenize using Byte-Pair Encoding BPE for subword representation. Model development. Encoder embeds input tokens, adds positional info, uses multi-head self-attention. Decoder, masked self-attention plus cross-attention to encoder output, generates target tokens iteratively. Prediction head, converts embeddings to token probabilities. Training and sampling. Pretraining, unsupervised MLM on multilingual data. Fine-tuning, supervised on bilingual or multilingual datasets. Inference, beam search or stochastic sampling for translations. Evaluation, offline metrics like BLEU, ROUGE, METEOR, plus online user feedback. System design, two-stage pipeline, language detector plus translation service with beam search. By combining these steps, Google Translate delivers fast, accurate, and fluent translations across multiple languages. The problem is to design Google Translate between different languages. What languages shall we focus on? Do we have enough data to train? Will the user specify input language always? Is there a constraint on the length of the user input? Shall we support translation where there's no internet? When designing Google Translate, the core machine learning problem is to map a sequence of words in the source language to a sequence of words in the target language. 1. Input and output. The input is a sequence of words in the source language, such as English. The output is a sequence of words in the target language, like Spanish or French. This output sequence may be of different length than the input, depending on the languages involved and the content. 2. Sequence-to-sequence model. To handle this mapping, we use a sequence-to-sequence, sec-to-sec model architecture, which consists of two main parts. The encoder processes the input sequence and compresses the information into a set of context vectors that capture the semantic and syntactic information of the source sentence. The decoder then takes these context vectors and generates the output sequence word by word, predicting one token at a time conditioned on the previous tokens generated. Third transformer with attention. Modern systems like Google Translate use transformer models that implement an encoder-decoder architecture with a powerful attention mechanism. Attention allows the decoder to selectively focus on relevant parts of the encoded input sequence at each step of generation, improving translation quality especially for longer sentences and complex structures. By framing translation as a sec-to-sec problem solved with encoder-decoder transformers, we enable efficient, scalable, and accurate multilingual translation. Data preparation is a critical step to ensure the translation model receives clean, consistent, and meaningful input. 1. Text. Pre-processing. Real-world language data often contains missing or noisy elements such as incomplete sentences, typos, or inconsistent formatting. Handling these issues up front helps improve model accuracy. Special attention is given to named entities like person names, locations, and dates, which often require special treatment to avoid mistranslations or loss of meaning. We apply normalization techniques such as lowercasing text to reduce vocabulary size and handle case-insensitive languages, stop word removal to focus on content words, though this is sometimes language-dependent, stemming and lemmatization to reduce words to their root forms, helping the model generalize better across morphological variants. Second, text tokenization. Instead of word-level tokenization, Google Translate uses Byte-Pair Encoding BPE, a subword tokenization technique that iteratively merges frequent pairs of characters or character sequences to build a vocabulary of subword units. This approach effectively balances vocabulary size and coverage, allowing the model to handle rare or out-of-vocabulary words by breaking them into meaningful subword units. BPE tokenization improves translation quality, especially for morphologically rich languages, or when translating between languages with vastly different vocabularies. By carefully pre-processing and tokenizing data, we prepare a high-quality, efficient input representation that enables the translation model to learn accurate mappings between languages. At the heart of Google Translate is a powerful encoder-decoder transformer model designed to convert sentences from a source language to a target language with high fidelity. Let's break down the architecture step by step. Encoder-the-encoder processes the entire input sentence all at once. Each token in the input sequence is first mapped to a text embedding, which is a high-dimensional vector capturing semantic information about the token. Since the transformer architecture lacks inherent sequential order, we add positional encodings to these embeddings. These can be either fixed sinusoidal functions or learned embeddings, providing the model explicit information about the token's position in the sentence. The sequence of embeddings is fed through multiple stacked transformer blocks. Each block contains multi-head self-attention layer. This layer allows each token to attend to every other token in the input sequence simultaneously, capturing dependencies regardless of their distance. Multiple attention heads enable the model to learn different types of relationships in parallel, such as syntactic and semantic connections. Feed-forward neural network. Following the attention layer, each token embedding is independently transformed by a two-layer feed-forward network with a ReLU activation, allowing the model to capture complex feature interactions. Residual connections and layer normalization are applied at every step to stabilize training and improve gradient flow. Decoder. The decoder is responsible for generating the translated output sequence one token at a time in an autoregressive manner. Like the encoder, it begins by embedding the target tokens, previously generated words, into vectors and adding positional encodings to maintain order information. The decoder transformer blocks are more complex because they integrate three types of attention mechanisms. Masked multi-head self-attention. Each token attends only to tokens before it in the output sequence, ensuring the model cannot peek at future tokens, preserving the autoregressive property. Cross-attention layer. This unique attention layer enables each output token to attend over the entire encoded input sequence, effectively aligning the generated translation tokens with the relevant source tokens. This is crucial for capturing long-range dependencies and nuanced translation relationships. Feed-forward network. Similar to the encoder, a feed-forward network applies nonlinear transformations to each token, embedding independently. As with the encoder, residual connections and layer normalization are applied after each sublayer. Prediction head. After processing through all decoder layers, the resulting embeddings are passed through a linear layer, followed by a softmax function, called the prediction head. This layer computes a probability distribution over the entire target language vocabulary for the next token to generate. The token with the highest probability, or sampled according to a strategy, is selected and appended to the output sequence. This process repeats until an end-of-sequence token is produced. Summary of encoder-decoder differences. The encoder's self-attention is unmasked, allowing full access to all input tokens simultaneously. The decoder's self-attention is masked to prevent future token access, preserving generation order. The cross-attention layer is only present in the decoder, connecting source and target sequences. Only the decoder contains the prediction head, responsible for generating tokens. This architecture effectively models the complexities of human language translation, by learning to represent both source and target sentences and how they relate, enabling Google Translate to produce accurate and fluent translations across many languages. Google Translate's success relies on carefully designed training and sampling strategies to handle multiple languages and generate accurate translations. Unsupervised pre-training. The initial training phase is unsupervised pre-training using a massive multilingual corpus of general text data. This stage helps the model learn universal language representations across many languages without needing labeled translation pairs. The core objective is masked language modeling, MLM. During training, a random subset of input tokens is replaced with a special left bracket mask right bracket token. The model's task is to predict these masked tokens correctly using the surrounding context. The encoder receives the masked sequence, learning to build contextual embeddings despite missing information. Simultaneously, the decoder is fed the unmasked sequence shifted right by one position with a start token, and it attempts to predict the next token at every step. The cross-entropy loss is computed only for the masked tokens, measuring the difference between the predicted probabilities and the actual tokens. This focused loss guides the model to understand language structure and context deeply. Supervised fine-tuning. After pre-training, the model undergoes supervised fine-tuning to specialize in translation. There are two common approaches: bilingual models, trained specifically for each language pair, focusing on maximizing accuracy for that pair. Multilingual models, which handle multiple language pairs within a single shared model, promoting parameter efficiency and cross-lingual transfer learning. Fine-tuning uses parallel bilingual data and continues to optimize the model with the next token prediction objective, again using cross-entropy loss. This step adapts the pre-trained model to translation tasks, improving accuracy and fluency in target languages. Sampling for translation generation. During inference, the model generates translations by predicting one token at a time based on the input sequence and previously generated tokens. Deterministic sampling, such as beam search, explores multiple candidate sequences to find the most likely translation, balancing quality and diversity. Alternatively, stochastic sampling introduces randomness, which can increase diversity and creativity, but may reduce consistency. This combination of robust pre-training, targeted fine-tuning, and sophisticated sampling enables Google Translate to produce high-quality, contextually appropriate translations across many languages. Evaluating the quality of Google Translate involves both offline and online metrics to ensure accuracy, fluency, and user satisfaction. Offline metrics. These metrics assess translation quality on benchmark datasets without involving real users, allowing rapid iteration and model improvement. BLU, Bilingual Evaluation Understudy, is one of the most widely used metrics. It compares the overlap of n-grams between the machine-generated translation and one or more reference translations, providing a score that approximates human judgment of translation quality. Higher BLEU scores indicate closer alignment with human translations. ROUGE, Recall-Oriented Understudy for Gisting Evaluation, measures overlap, mainly focusing on recall of n-grams, often used for summarization, but applicable to translation evaluation as well. Meteor, metric for evaluation of translation with explicit ordering, improves on BLEU by considering synonyms, stemming, and word order, providing a more nuanced evaluation of semantic accuracy and fluency. Online metrics. Once deployed, Google Translate relies on user interaction data to assess real-world effectiveness. User feedback and engagement track how often users accept, edit, or reject translations, as well as explicit ratings or comments. This direct user input is invaluable for identifying weaknesses and guiding future improvements. Together, offline and online metrics provide a comprehensive understanding of translation quality, enabling Google Translate to evolve continuously and better serve users worldwide. The overall system design of Google Translate can be thought of as a two-stage pipeline: language detection and translation. Language detector. The first step is to determine which language the input text is written in. This is formulated as a sequence classification task. We use an encoder-only transformer architecture, similar to BERT, which reads the full text and produces contextual embeddings for each token. There are two common approaches to aggregate these embeddings into a single prediction. Average pooling. Take the average of all token embeddings from the encoder output, then feed this representation into a classification head that outputs probabilities over possible languages. Last token representation. Alternatively, we can take the embedding of the final token in the sequence, which has aggregated context from the entire text, and feed it into the classification head. The output is a probability distribution over supported languages, and the highest probability language is chosen. 2. Translation service. Once the source language is identified, the system passes the text to the translation model, which uses a sequence-to-sequence transformer with an encoder-decoder architecture. To produce high-quality translations, we use beam search, a deterministic decoding strategy that explores multiple possible translations in parallel before selecting the best-scoring one according to the model's probabilities. Finally, the generated tokens in the target language are detokenized and joined back into natural text for the user. In essence, this architecture ensures that Google Translate can seamlessly handle unknown input languages, select the right translation path, and generate fluent, context-aware translations.